Hello and welcome to this lecture. So far we've been looking at two sort of vector spaces, mainly Rn and Cn, right? So the real vector space with dimension n, and or more generally the complex vector space with dimension n. We saw a lot of properties of that. We saw a lot of utility of that, applications, all sorts of interesting special cases, eigenvalues, symmetric matrices, normal matrices, all of that. Now we're going to do a slightly different step and think about discrete time signals and continuous time signals as vectors. Okay, so you may be used to thinking vectors as a list of numbers, either 3, 4, 5, etc., finite number. Now we want to think of the entire continuous time signal as a vector. Okay, so this is a very slightly different way of thinking about it, but it's very powerful in all of electronic system design. So if you can think of the signal as a vector, you get tremendous intuition about it, and you can use that intuition in designing systems and all of that. So it's a very important idea. Let's look at that next. Okay, so here is the sort of a starting point to think of how a signal becomes a vector. Okay, so we are used to vector being a list of values, right? So how do you go from signal to a list of values? So this is how you think about it. These are just intuitive, very high level ideas just to get you to grasp how a signal can become a vector, and then we'll make it a little bit more rigorous and make it more clear. Okay, so let's start with a signal or a x of t. See, what is a signal? Signal is basically a function of time, right? Function of one variable, and that variable usually we keep as time t. It can be any other variable also, but usually we denote it like that, x of t. And then it is some function, right? So I've shown you one illustration here. You may be interested in a certain time interval 0 to t, or this interval can be anything else also, right? I'm just picking 0 to t for convenience. So let's look at a signal x of t from 0 to t. Okay, so what is the meaning of that? For any particular value of t, x of t is also the value of the signal at time t. That's how one thinks of this function of one variable or signal, as we call it. Okay, so now what you can do to think of how to convert this into a vector is the following. Is just a rough intuitive idea to get you to think about it. Typically when we think of a vector, we think of like n values x1 to xn, right? So this is what we associate with as a vector. Now how does this become a vector? You can do the following. What you can do is you can sample, right? So you can take this interval 0 to t and then take n samples of points here. So at time 0, ts, 2 ts, so on till n minus 1 into ts. What is my ts? It's like my sampling time, sampling clock. I make it t by n. Okay, so I get here n points. These are all values taken by this signal or this function at different points here. So this you can claim is a vector. This vector is derived from the signal, but this vector doesn't really represent the whole signal, right? There are a lot of gaps in the middle, right? So how do you reduce these gaps? You can do this thing, but that gap is there. But nevertheless, you can think of this vector as approximating the signal, and one can do something like this. For between I and its and I plus 1 ts, right? So that gap we don't know what the signal is. Okay, you can think of sampling and holding. So you sample at its and sort of hold. Okay, so you get a discrete time approximation for the signal x of t. Okay, so this vector definitely represents that approximation. It is an approximate representation of the signal and not an exact representation of the signal. But that's okay. Maybe we can live with that approximation because it gives us a lot of benefit to think of something as a vector, right? But later on, we will sort of get over this little bit of approximation issue. But this is one way in which you can quickly think of how, even though we think of x of t, t being a real valued variable, we think of a continuum there. You can sort of approximate it like this and think of it as a vector also, if you allow for that approximation. So here is a simple example of the sample and hold. If you were to sample and hold, you will actually have this signal, this red signal, and not the white x of t. But it's as n becomes larger and larger, you can imagine if the x of t is reasonable, you will get something closer and closer to this white, and we are okay with that, right? So that approximation we are okay with. So basically, when n becomes infinite, okay, very large, this vector can be expected to be sort of close to x of t. So one little hint of an idea that we are getting here is, if you want to represent a signal with where the variable you're thinking of as real valued, taking a continuum of values, then you have to think of infinite number of coordinates in your vector. Okay, so the dimension has to go towards infinity. Okay, it cannot be finite dimension. So that is the first big step when you go from RNCN, which is n dimensional vector space, to signals being vectors. You'll have to go to infinite dimensions in the vector space, because you can clearly see that n has to go to infinity to really represent the x of t, right? In fact, maybe even a different type of infinity, who knows, but this is it's going to be really large. Okay, so this is one little thing, but this is good enough. I mean, you can see how the vector sort of enters the picture here. For every value of t, you just sort of enumerate all the x of t. Of course, it's real valued, but still enumerate as much as possible, and then you get a representation for x of t. So this is sort of one way to think about it, but we'll think about it slightly differently. But nevertheless, this is a good intuition to have if you want to think of x of t as a vector. Okay. So basically, how do you think of vectors of infinite length? So in some sense, these vectors, when you think of signals as vectors, they're going to have infinite dimension. They're going to live in some infinite dimensional space. It's not a finite dimensional space. So let's think of a vector with infinite number of coordinates. That's the first thing to think about, right? You should get comfortable with that. Okay. So what you can think of as a vector here, A, is A1, A2, An, and it goes on and on and on forever, right? And these AIs are complex valued. It could be real also, but we keep usually our examples will be real, but we'll generally think of the AI as complex also. This is actually a sequence, right? You remember your math 1, we were studying these sequences. So I'm representing this entire sequence, or I'm calling this entire sequence as a vector A. Okay, so this has got like infinite number of coordinates, so the dimension is infinite, the vector is long forever, goes on forever, it doesn't stop, but we can still think of this as a sequence. Okay, and we have studied sequences, we know a lot about what happens to the limit, what happens for large n and all of that. So we have various characterizations of how a sequence behaves. So we can think of this as a vector. Okay, there's no problem with length going to infinity as such, right? So vector is a vector. Now, what do you do with a vector? There are two important operations for any vector, right? You should be able to add vectors and get another vector, add two vectors and get another vector. You should be able to scale a vector and get another vector. So those are the two fundamental operations in a vector, in a vector space, right? If you can do that with vectors, then that's okay. Infinite length is also okay. How does it affect us, right? So it doesn't affect. So let's first check if those two are possible, and those two are easy, right? If you want to do vector addition, you have a sequence A and you have a sequence B. I know that I can add sequences, right? So you just add the corresponding element, and this also becomes an infinite length sequence. So addition is trivial, right? So there's no real problem with addition. Same thing with scalar multiplication. You have a sequence A, you want to multiply it with a scalar C, you multiply each coordinate or each value in the sequence, each AI in the sequence with this C. So you get another sequence. So addition and scalar multiplication is no big deal. Another thing about the vector space is you need a zero element. So of course, zero element is also there. You take the zero vector to be all zero sequence, right? So you see that whatever you were doing, the elementary operations you are doing with vectors, you can do it even if the length goes to infinity. Nothing is affecting you because of the infinite length. Just addition, scalar multiplication, zero vector, you can do. Okay, so you can think of even with infinite length the thing as vector. It's not too wrong. Okay, so these kind of vector spaces, okay, to distinguish them from Rn, Cn for a finite n, we call them sequence spaces. Okay, so when you have a1, a2, an, so on for going off up to infinity, these are called sequence spaces. Okay, there are specific types of sequence spaces that we'll be interested in, but in general, these are sequence spaces and they have properties of vector spaces. Right? So some of the properties are there. Of course, dimension goes off to infinity, so that rules out some of the interesting properties. You can think about what it rules out. We're not going to go so deep into the theory side here, but at least from a high level, you can think of infinite length sequences as vectors. Okay. Okay, here are some examples. So let's see if we can derive some infinite length vectors from signals, right? So let's see if we can do that. We have signals from 0 to t here, and I'm going to think of them as vectors by sampling these signals, at t by 2 at length epsilon, at intervals of epsilon I'm going to sample. And then I will send this epsilon to 0 to make it larger and larger in some sense, right? So you can see you may have a constant signal, x of t is some value c over this entire thing. And for this, you will get a constant sequence, right? C, 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 always throughout, right? For every sample you do here, you'll get a C. You may have a signal x of t is t, and if you do this sampling sort of technique to get an infinite sequence here, you will get t by 2 minus epsilon, t by 2 plus epsilon, minus 2 epsilon, plus 2 epsilon, all the way down to 0 here and all the way up to t here, right. So, you will get that as the sequence. So, you may also have a more complicated looking signal like sine 2 pi k t by t, where k is an integer. You can see this is a sinusoid, and by from t equals 0 to t equals t, it does k cycles of the sinusoid, right. So, 2 pi k. At t equal to 0, it is sine 0. At t equals capital T, it has gone to 2 pi k, the phase has gone to 2 pi k. So, k cycles it has gone through. So, it will have k cycles of the sinusoid from 0 to t, okay. So, that guy also you can sample. So, if you put t by 2 here, you are going to get pi k and then pi k into 1 minus 2 epsilon. You can just sampling this at t by 2 minus epsilon, t by 2 plus epsilon, you get this signal. So, you can get these strange looking sequences from sampling of signals, and you can go on and on with this example. So, and then you can see as epsilon tends to 0, these two things sort of look to be the same. So, you can think of, you can sort of motivate yourself that you can approach these kind of signals as sequences also, okay. But but I want to let you think a little bit more abstractly, okay. It's fine, sequences are nice, you can think of signals as infinite length sequences by sampling them finer and finer, yes, it's good, but you don't really have to do that, right. So, you can sort of abstract the picture a little bit. Who said vectors have to be defined as a list of coordinates, right. So, don't think of that, just define vectors as any object with which you can do addition and scalar multiplication, okay. So, let us say a vector is more abstract, it can be anything, any object like signals x of t's can be vectors, I am not going to roll it out, but the only thing I should be able to do with them is I should be able to add them, I should be able to do scalar multiplication, okay. So, that is also possible with the signal x of t, right. You do not have to necessarily think of sequence to go from signal to vectors, right. So, if you just take this x of t, it's say complex valued, it could be real valued also, but I am taking complex valued here. This is actually a function of one variable, right. So, you can recall all its properties from math 1. We studied so much about x of t, what to do with it, differentiate, integrate, of course, not with complex valued, real valued usually, but complex valued is not a big problem. Complex valued is just a real value plus imaginary value, right. So, when it is complex valued, you can write it as x1t plus j x2t. So, think of x1t, x2t, both are real valued. So, you can deal with derivatives of those functions, you can integrate, you can take limits, you can think whether it is continuous or not, all of those properties you can think of. So, x of t is an object we know very well. Now, I want you to think about, abstract a little bit and think about this object itself as a vector. Now, if this object has to be a vector, I should be able to add, and of course, I can add, right. If I have two functions x of t, y of t, I can of course add them, I get a well defined function, there is no problem there. I can do scalar multiplication. If I have a function x of t, I multiply with a scalar c, I get a well defined function. So, I do not go outside of this space. When I have a function or a signal, I can do addition, I still get a function of the signal, I can do scalar multiplication, I still get a well defined function, no problem. And there is also a 0 vector, right. So, the 0 function which assigns 0 for all t is the 0 vector, okay. So, all the properties that you expect from a vector space are typically, are easily satisfied. The axioms are satisfied if you want to go axiomatic in your definition, they are all satisfied. So, you can think of a collection of functions also as a vector space in that sense, okay. Once again, not very rigorous, but from a high level to motivate you thinking about signals as vectors. So, these kind of spaces, so previously we saw these infinite sequences forming sequence spaces, and there you could add sequences, multiply sequences with scalars. Now, we are seeing just with functions directly, you can add functions, you can multiply function with a scalar, you have a 0 function. So, you can think of these functions as vectors, okay. So, is there a point to doing all this? I'll show you the power of these kind of ideas. This abstractness in thinking of vector spaces with different objects is very, very powerful, and we'll see that as we go on, okay. So, there are two basic spaces that we are seeing. One is a sequence space. We will not study sequence spaces too much in this class, it's not so relevant to us. What's really relevant is function spaces. So, we'll study function spaces quite closely, a little bit more closely, okay, not too much, but we'll study function spaces much more, because functions correspond to signals for us, and signals appear in electronic systems, and so we should understand them as much as possible, okay. Okay, so here is a particular change here. So you can look at, of course, all possible functions, and then that will also be a proper space. But I want to show you how you can specialize to a particular domain. So here I have specialized to a domain 0, t. Of course, you can specialize to any other domain. Okay, so you can say any subset of the real line. You can take a, b, minus 1, 1, 0, infinity. Of course, you can take the whole real line. You can take any domain here and say, I'm worried only about those functions which exist from this domain to complex numbers. Okay, so it's a function of one variable from 0, t to c. I don't care about the other parts. If you say that also, these type of functions also can be thought of as vectors. It's very easy to see, right? So when you do addition, x of t plus y of t is a function from 0 t to c. If you do scalar multiplication, again a well-defined function from 0 t to c. So this closure under addition and scalar multiplication happens for various objects. Okay, it's all interesting to see that. You also have the 0 vector. So this also satisfies all vector spaces. So instead of thinking of all sorts of functions, if you're only interested in functions which have a domain 0 to t, that's also great. That is also a function space. So you can think of these kind of modifications, and we'll look at these kind of specific modifications later on. Okay. So you may ask, okay, what do I do with these sequence spaces and function spaces? Sequence space is also very useful, but in this course we will not be looking at it so easily, so much in detail. But if you go to a DSP, discrete time signal processing course, a digital signal processing course, there you will see discrete time signals, right, that go on forever or two-sided, one-sided. They actually are infinite dimensional, right? So they can go on and on and on forever, can be infinite and long. To model those kind of things, you can use sequence spaces and argue based on sequence spaces. We will do a little bit, but not too much of that. Okay. But what's more interesting to us in this course is these function spaces. So x of t we can think of as function, and these kind of correspond to continuous time signals. So the signals in electronic systems, whether they are discrete or continuous, are well modeled by sequence spaces and function spaces, and that's the direct connection to why we are interested in these things. Okay. So both can be vectors in a sequence space or function space. So now if you go back and think about our finite dimensional vector spaces, right, R and Cn, really what got us going were operators, right, matrices, the transformations, and even the inner product. The inner product was a very powerful construct, right? So when we had the inner product, we could think of angles, lengths, magnitudes, and we could use that very, very nicely to understand operators better. We had this orthonormal basis, which was really, really powerful. All of that was possible. So how do we think of matrices or operators in function spaces particularly? How do we think of inner product in sequence spaces, function spaces? Okay, so we have to construct these things. So in finite dimensional spaces, we could construct some of them. How do we think of them in these large infinite dimensional spaces? Okay, so we will in the beginning we'll sort of consider how to define sequence spaces and function spaces. This is how the rest of the lectures are going to be planned. We'll figure out how to define inner product for functions and signals, and from there we will go to orthonormal basis for signals, and then, well, sort of orthonormal basis for subspace, signal subspace, and from there we'll move towards ideas like Fourier series, which have played a monumentally important role in all of electronic system design. Okay, so that concludes this lecture. Thank you very much.